So, good evening, viewers. So today we're going to talk about the sine rank test or the Wilxocon sine rank test. And my name is Nicholas Kinagawa, a lecturer at Boston University in the Department of Mathematics and Statistics. So basically today we are going to prove this assumption that another assumption required by the sine rank test or the Wilxocon sine rank test, that the sum of positive differences is a value of a random variable with a mean mu, which is n into n plus 1 over 4, and the variance sigma squared of n into n plus 1 into 2n plus 1 over 24. And I'm going to prove this one. So without wasting time to prove this, we are saying since the rank sine test or the sine rank test or the Wilxocon rank sine test is based on the assumption that the sum of positive differences, which is t, and the sum of negative differences, which is t minus, we are going to base this statistic that when you have the t, which is t plus or t minus sums, they have the same assumption and the hypothesis will also be the same. So expressing the statistic, the t plus or t minus in terms of the ranks and sign differences, the null hypothesis of either a one sample sine rank test or a paired sample sine rank test may be given as follows. And this can be given as that for each rank, the probability that it will be assigned a positive difference or a negative difference are both half. And thus we can write that random variable t plus as a given rank times the random variable plus the second rank times this random variable up to the nth rank times this random variable, where all the random variables are independent random variables with a boundary distribution. So to prove the assumption, we're going to prove basically based on the assumption of the mean and assumption of the what? The variance. So since all the random variables are from a boundary distribution with theta, which is a half, the mean of a random variable from a boundary distribution is the same as p, which is the same as half in this situation, and also the variance of a random variable from a boundary distribution is pq, which is the same as half times half, which is 1 out of 4. So on the assumption that the mean is equal to x, f of x, and since there are very many random variables, we shall basically look at the sum of the first up to the last random variable times this distribution, which is f of x, and also the variance, which are based on the x squared f of x. And since these are different random variables, n random variables, we shall also look at the sum of the squared rank times this what? Probability of happening. So the expression of the random variable, which is the mean t plus, the same as the first rank times its corresponding random variable up to the nth rank times its corresponding random variable. To prove this, we are going to introduce an expectation both sides, both on the right-hand side of this expression and the right-hand side of the what? Of the next expression. So when we introduce the expectation on both sides, we are seeing that we shall be having if et, which is equal to the mean, which is the same as e into 1 plus x1 plus 2x2 plus 3x3 plus up to n xn. And we are saying that when you enter the expression into the expression, it will give us 1 times the stated value of x1 plus 2 times the stated value of x3 2 up to n times the stated value of xn. And we saw that since these are independent random variables from a boundary distribution, the stated value of a random variable from a boundary distribution is equal to p or theta, which is a half. So substituting for half in the next equation, it gives us that e of sum of squared positive differences will be equal to the mean plus the first rank times the probability of each happening, which is half, plus the second rank times the probability of each happening, which is half, up to the nth rank times the probability of each happening, which is also a half. And it is evident from our formulas here above that a half is a common value, and so it's better we bring it out and we form others into the brackets, which will be 1 plus 2 plus 3 up to n terms. And the expression in the brackets is similar to the sum of n random n natural numbers. So to derive a simple expression for the n1, the sum of n1 n natural numbers, we begin by, if you assume that their summation from 1, 2, 3, 4 up to n, and of course you can start the second term to be n minus 1. Because if you have 10, the second term to be 9, which is 10 minus 1, gives us a first term. It can be reversed that if you begin with the last term in the first equation, which is n minus 1, n minus 2, n minus 3, up to 2 plus 1, which is from the reversing the first expression x2, it gives us that if you do add these two equations, the first term will be n plus 1, n minus 1 plus 2, which is the same as n plus 1, n minus 2 minus plus 3 is the same as n plus 1, add up to the last term, which will be n plus 1. And also the sum of two s's gives us twice the sum. And this is evident that the sum of n constant numbers is the same as n in that term. So that's why you are getting the same as the sum of k constant terms is nk. Thus, we shall have n into n plus 1, which is equal to twice the sum. And since we are solving for the sum, we have s will be equal to divide by 2 both sides. We get the sum of n natural numbers as n into n plus 1 over 2. So when you substitute by this sum into the expression of the stated value of the sum of positive differences, it gives that the stated value of t plus is equal to mu, which is equal to the same as 1 out of 2 times the sum. And by substituting for s, or the sum of n natural numbers, we get out that the mean of random variable of squared differences is equal to et, which is the same as n into n plus 1 over 4. And this is similar to the expression which we are trying to prove. And in the preceding slide, we are going now to prove the variance of this random variable because we are trying to test an assumption. So to prove this, we shall introduce. So to prove this, we shall first discuss briefly about the variance and its expressions. So the random variable of t plus is given in that form again as the rank times its corresponding random variable which has an independent binary distribution. And if you introduce the variance on both sides, give that the variance of that random variable will same as the variance of the whole bracket or the whole expression. And we know that from properties of variance, it is seen that the variance of x plus b is same as a squared variance of x plus variance of b, but the variance of a constant is known as 0. And also showed that the variance of any random variable which follows a binary distribution is pq, which is in this case shall have a half times half, giving us 1 out of 4. So expanding the expression of the variance into the expansion of half, we shall have that the variance of t plus will be equal to the variance of the first rank times the random variable plus the second rank times the random variable plus up to n times xn, which is the random variable. So the variance of t plus will be the same as 1 squared from the property of variance, 1 squared variance of x plus 2 squared variance of x2 up to n squared variance of xn. And you can see that from this expression the same as 1 squared times a quarter, because a quarter is the variance of that random variable, and all random variables have the same variance since they are all following a binary distribution. And from this expression, it is evident that 1 out of 4 is a common factor which can be ruled out, and shall have that 1 squared plus 2 squared up to n squared, which is an expansion of the sum of squares of the sum of first n squared numbers. So to deal with this expression in the brackets, we shall introduce a summation of that the sum of n numbers, the sum of n powered numbers. So if you begin by a certain expression that if you want to sum when numbers are powered to 0, so the sum of n numbers powered to 0 is the same as n, because any number the power 0 is 1. And when you say that n is equal to 2, the sum of n numbers power 1 is the same as 1 plus 2 plus 3 plus 4 up to n plus 1, which is the same as 1 plus 2 up to n. And this has been proved from the previous example using the sum of n first natural numbers, and we got S1 will be n into n plus 1 over 2. However, the complex part of this expression is on S2, which is sum of squares of the natural numbers. So to deal with this, we shall of course introduce an expression that n plus 1 cubed, n plus 1 bracket cubed minus n3. If you simplify this one, the right hand side gives us n cubed plus 3n squared plus 3n plus 1 minus n cubed, and which is can be further simplified at n plus 1 cubed minus n cubed as our left-hand side and 3n squared plus 3n plus 1 as our right-hand side. And if you consider substituting for n from the n0 terms up to k minus k terms, we shall yield an expression which are further divided into a table for easy expansion. And this is the table below. We are saying that for n equal to 1, you substitute for 1, you have 2 cubed minus 1 cubed on the left-hand side. On the right-hand side, you have 3 into 1 squared plus 3 into 1 plus 1. For n2 is the same as 2 plus 1 cubed, which is the same as 3 cubed minus 2 cubed equal to the same as 3 into 2 squared plus 3 into 2 plus 1. And for n power n equals to 4, it will be n plus 1 will be 4 plus 1, giving us 5 cubed plus, as you can see from the expression. And of course, we know that we have summing up to n terms. So the second term was given as n minus n is what here? Minus 1. But if you substitute into the formula, it is evident that you can see that we shall have k minus 1 plus 1 is the same as k cubed. On the next expression to be k minus 1 cubed. And on the right hand side to be k minus 1 squared plus 3 into k minus 1 plus 1. Thank you, which is very good also. However, our last term will be k plus 1 cubed plus k minus k cubed equal to 3k squared plus, and you simplify like further. So you can see that if you cater for the right hand side and the left hand side separately, you can see that both 2 cubed minus this will cancel if you do the summation. And should be the last term, which is k plus 1 cubed, and the first term, which is 1 cubed, and this will be on the right, on our right hand side. Also, we shall also later come to 3. And 3 will give us, it will be 3 into 1 squared plus 2 squared plus 3 squared up to k squared. And this gives us S2, which we're trying to prove. And the third expression gives us 3 into 1 plus 2 plus 3 up to k, which we already had at the sum when n is equal to 1. And also 1 plus 1 up to, which is same as S of 0, which is n. We shall also let us see that when you continue to simplify it, is that k plus 1 cubed minus 1 cubed will be the same as substituting for the missing terms or the constant terms, which we can say that for 3 into 1 squared, for 3 into 1 squared plus 2 squared up to k squared, this gives us what? 3s2, and also plus 3 into s1, and also s0, which is n. And of course, we are just basically what? Simplifying for some of the functions which we already had. And if you do substitute for s1 and s2 into this expression, it gives us k cubed plus 3k squared plus 3k, which is, and plus 1, which is the expansion of k plus 1 cubed minus 1 cubed. For that will give us 1 minus 1 gives 0. And on the right hand side, we shall have 3s cubed, 3s squared, 3s2 plus 3k into k plus 1 over 2, which is sum of n terms, power 1, of course. Then also we have s0, which is sum of 1 plus 1 up to n, which should be k times. So if you try to remove the fraction into the expansion, multiply by 2 both sides, and this here is 2k cubed plus 6k squared plus 6k equal to 6k squared plus 3k squared plus 3k plus 2k. When you continue to further simplify this one, we are finally seeing that to be 2k cubed plus 6k squared plus 6k equals 6k squared plus 3k squared plus 5k. And 2k cubed plus 3k squared plus k is equal to 6s2. And of course, you can say if you factor out k, it is k into 2k squared plus 3k plus 1 is equal to 6s squared. And remember, we're aiming at s2, so we divide by 6 both sides, and this gives us our next t, and this gives us our next expression. And you can see that we shall have a function which we need to be simplified, this one, and we shall basically use a quadratic formula to simplify this. And this is a quadratic formula with a, which is 2, b, which is 3, and c, which is equal to 1. And using the quadratic formula of negative b 2 plus or minus root of b squared minus 4ac over 2a to give us what you can see here. And this thing everyone can be able to simplify this further. And you can see that if the first terms will be k can be -1 or k can be a half. So when we try to form factors, we should find that k equal to -1 is same as k plus 1, and k equal to -1 is same as 2k plus 1. And this can be substituted for k plus 1 into 2k plus 1 into s2. And this is, after getting for the function of s2, we come and further substitute for the sum of squared n natural numbers into our expression of the variance, and this will lead us to the expansion above, hence problem. Thank you for watching. Meet in the next video.